Welcome to another podcast number 13 in a long line of chapter 18 podcasts. Again, longest chapter of the semester. Here we're going to look at calculations using buffers. So we're going to tie in a lot of the stuff that we've done with our buffers thus far and put them into this podcast here. Well, let's start here with sample problem 18-14, and we still have another sample problem in this podcast to do as well, but in this one where you have a buffer, it is 355 mils of both 0.2 molar NaHCO3 and 0.134 molar Na2CO3. So it's sometimes hard for us to spot this, but in this case, this is going to be our weak acid, and this is going to be the weak base in our buffer. All right, they both have sodiums there that are going to be spectator ions, and so the things that are left over are going to be either our acid and base there. So first off, it wants us to calculate the pH of our buffer. So what we need to do is we are going to either find the concentrations of each or the number of moles of each. And right, remember, I see the word buffer. I know I'm going to use my equation that I use for every buffer problem. So in this case, I'm just going to go ahead and find the number of moles of each. You could do it either way, right? But I'm going to do the number of moles. So the number of moles of my HCO3 minus is going to be, all right, it is 0.355 liters, and it is 0.2 molar. So we end up with 0.071 moles of the weak acid part. Next, we're going to do the same thing for the CO3 2 minus, right? So again, it is also 0.355 liters, but it happens to be 0.134 moles per liter, and so I get 0.0476 moles of that one there. So now I can plug into my equation, which is H plus is equal to my Ka times the number of moles of the acid part divided by the number of moles of the base part. All right. If you were to work this problem on an exam or somewhere else, you'd have to be given this. I had to look it up. And so I looked up what the Ka for the HCO3 is, and it happens to be 4.7 times 10 to the minus 11th. And then we've got our 0.071 divided by our 0.0476. And so I have 7.0 times 10 to the minus 11th is my H plus. And so the pH is the negative log of 7 times 10 to the minus 11th. And I get that to be 10.15. All right, I bet money that this problem on the next slide is going to have us see what happens to the pH of this when we add either a strong acid or a strong base to it. So let's go check that. Well, call me shocked that we are going to find the pH of the buffer after we add in some strong acid. So we have to remember what happens when I add a strong acid to the buffer. Right? The strong acid is going to convert our weak base to weak acid. All right, and so to do that, we need to calculate the number of moles of each after we add in the hydrochloric acid. All right, so let's see. Right, we start with calculating the number of moles of my weak acid. All right, I started with 0.071 moles of it, right? That was from part A of the problem. We are making weak acid, and we are making 0.03 moles of weak acid because the weak acid's converting 0.03 moles into that. So we get 0.101 moles of that. Now we're going to find the moles of our carbonate. Okay, well, we started with 0.0476 moles of it. It is going down by 0.03 moles because we're adding acid and the acid is reacting with that. And so we end up with 0.0176 moles of that. So now I have my new ratio of moles. We're just plugging into our equation for solving for a buffer. Right? But now we have just a new mole ratio in there. So our H plus is equal to 4.7 times 10 to the minus 11th. And now we have 0.101 on top and 0.0176 on the bottom. So I get 2.7 times 10 to the minus 10th. So we can find the pH of this is now 9.57. All right, if we remember from the previous slide, we had a pH of the buffer being 10.15. Now the pH is 9.57. The pH has dropped, which makes sense. We added an acid to it, so the pH should go down. Notice it doesn't drop by a ton, but it does drop because it's converting the weak base into more weak acid. All right, well, part C of the problem is a lot the same, except for we are adding now 0.03 moles of, all right, strong base. So remember, right, a strong base is going to convert our weak acid to weak base. So the weak acid, right, is going to decrease, and the weak base is going to increase by that amount. So we're going to do this. We're going to start with our initial amounts that we add. So again, right, number of moles of my HCO3 minus, we started with 0.071 moles. It's decreasing by 0.03. So it's going to be 0.041 moles. And the number of moles of the carbonate is, all right, we started with 0.0476. We're increasing by 0.03. All right, now we're plugging into our equation to solve for our H plus concentration. So we have 0.041 on top and 0.0776 on the bottom. And we get 2.5 times 10 to the minus 11th. And so the pH is the negative log of that, which is 10.60. Right? And again, right, we started with a pH of 10.15 for our buffer. When we added some strong acid, the pH went down. When we added some strong base, the pH went up. That should make sense. Just remember, right, which thing is going to increase and which is going to decrease when we add a strong acid or a strong base to our buffer. One more sample problem in this podcast. Here we have a buffer system, and it keeps our blood at a pH of about 7.4. We're given the Ka for the weak acid in that buffer system. I want to calculate the ratio of weak acid to weak base at a normal pH. All right. Well, I know first off, right, that with our normal pH, the H plus concentration is going to be 4 times 10 to the minus 8. All right, well, we can use that to solve for our ratio of acid to base, remembering that our H plus is equal to our Ka. See, I was not kidding. When we do buffer problems, when I see buffer, we're probably going to use this equation. And this is our H2PO4 divided by our HPO4 to minus. Okay, so this whole factor out here is our ratio. So we could say that our H plus is equal to our Ka times some ratio, right? And the ratio is what we're looking for in the problem. So if I solve for this, then I get that 0.65 is equal to the ratio of acid to base. Moving on to part B, right? Asks what percentage of our base are converted to acid when our pH goes down to 6.8. All right, this is going to be a little bit more complicated, so let's follow along and see what we're going to do. First off, we have to find a new ratio. So we're essentially going to do what we did from the step above, but we're going to do it for our new pH. And so again, I'm going to take 10 to the minus pH, right? And I'm going to get a new H plus concentration there. All right, and now we're going to say, all right, I have my H plus is equal to Ka times our new ratio. I'm just going to write ratio here, right? Okay, so our H plus in this case is 1.6 times 10 to the minus 7 is equal to the Ka, which is the same as it was above, 6.2 times 10 to the minus 8 times our ratio. And so our new ratio in this case is going to be 2.6. All right, now that hasn't really answered anything. All it tells me is that the acid to base ratio has changed to 2.6. All right, let's see on the next slide what we're going to do with that information. So what we're going to do is we're going to combine what we've found. And so it says up here that we're going to determine the percentage of ions converted. We will set the acid concentration from part A of our problem to be 0.65 and the base to be 1.0. All right, so if we recall, right, the ratio of acid to base was equal to 0.65 in part A. And so I can write that as being 0.65 divided by 1. Right? I could really write that in a heck of a lot of different ways. Right? I could write that as 1.3 divided by 2. That's the same ratio as 0.65 divided by 1, but I like to deal with the number 1 in places if I can, so I'm going to write it like this. Then I'm going to plug that in to the fact that I know that 2.6 is my new ratio of acid to base. So let's say that 2.6 is going to be equal to, all right, well, we had initially 0.65, and I know that as I decreased the pH, I am going to increase my acid amount by some amount divided by 1. All right, and if the acid part is increasing, then the base part must be decreasing. All right, so we know that because our pH is going down, that the acid's going up and the base is going down. All right, so now, right, we just have to solve for our x. So I'm going to get 2.6 minus 2.6x is equal to 0.65 plus an x. We're going to keep rearranging around, and I get that, all right, 1.95 is equal to 3.6x. And so our x is going to be equal to 0.54. All right, well, notice, since I kept the base equal to 1, 1 minus 0.54 is a decrease of 54%, and that's what the problem was asking for anyway. So we got that even though because we kept that as 1. All right, so that ends another podcast. Next up, we are going to look at acid-base indicators.